Hi, everybody. It's Professor Mitchell. And of course, we're here today to get started on Math 1610, Statistics for Decision Making, aka Business Statistics. So before we get started, I want to say that there are going to be a couple things different about this video. I don't want you to think that this is going to be how it always works. Number one, this video is going to cover all of Chapter 1. All right, and then moving forward, each video will just be one section of a specific chapter. It's not too uncommon for the first chapter in a statistics book to be pretty short. And the second thing I want to point out is that Chapter 1, which this is true in a lot of math classes, is a lot of vocabulary. So if you feel like I'm kind of reading from the PowerPoint, I want you to know that I won't be doing that as much in future chapters. I really don't enjoy doing that, and you will hear me, kind of put my own spin on things. But if it seems like I'm reading from the PowerPoint, I won't do that as much after we get out of Chapter 1, okay? So let's get started. There are 4 sections in Chapter 1. We have 1.1, Business Statistics and Their Uses, 1.2 on data, 1.3 on branches of statistics, and finally 1.4 on ethics and statistics. So starting in 1.1, Business Statistics and Their Uses, I have probably taught out of half a dozen different statistics books, and each one of them has their own definition of what is statistics. So I do like your book's definition. Statistics is the mathematical science that deals with the collection, analysis, and presentation of data, which can then be used as a basis for inference and induction. So those 3 parts of statistics, collection, analysis, and presentation, we're not going to cover them in that order. We're going to, I think, start with presentation and then talk a little bit about collection, and at the end, it will be a lot of analysis. Some examples of how businesses use statistics. Statistics is used for marketing research, advertising, operations, finance and economics, and finally weather. And you can read there about some of the details, examples within each of those categories. All right, and we're already on to section 1.2 on data. So data are values assigned to observations or measurements. And I want to point out, people commonly think of data as referring to numbers. Data does not have to be numbers, all right? For example, if I had a list of the students in this class, which I do, actually, and it said whether each student is a freshman, sophomore, junior, or senior, which it does, actually, that would be an example of data. Information is data that are transformed into useful facts that can be used for a specific purpose, such as making a decision. And we've got an example right here. So in this example, we have temperatures in New York City, near my home turf, in January of 2018. Notice that they give you a citation for where that data came from. That is a good practice in statistics. And so for the first 7 days of 2018, they're showing you the high temperature and the low temperature in New York City. So those temperatures would be an example of data. Each individual value is called a data point, or sometimes I just call it a value. Analyzing the data can provide information. So for example, somebody figured out that the weekly average low temperature in New York City that week was 9.3 degrees Fahrenheit. Fun fact, this is the lowest historical low temperature for New York City based on recorded data at this time. All right, a data set is a collection of data points A database is a collection of data points that contains multiple rows, which are sometimes called records, and columns, which are sometimes called fields. Sources of data, there's primary data, which is data that you yourself have collected for your own use. And then there's secondary data, which is data that's been collected by someone else. If you're an English person, you know, you're interested in the subject of English, kind of reminds me of primary sources and secondary sources. So primary sources are things like journals. They are the first to report the information. And then a secondary source might be something more like a newspaper that is reporting what was reported in the journal, all right? So primary and secondary data, it's kind of a similar concept. Some advantages and disadvantages of primary and secondary data. So of course, the advantage of primary data is that it's been collected by the person or organization who's going to use it. Disadvantage of primary data is that it can be expensive to collect your own data, and it can also be time consuming. So an advantage of secondary data is that it's readily available and less expensive to collect. But disadvantages, you have no control over how the data was collected, and it's less reliable unless you know that the data was collected and recorded accurately. So a couple things to think about when you're trying to decide whether to use primary or secondary data. Here are some examples of primary data collection methods. You have a direct observation or a focus group where you observe subjects in their natural environment. For example, watching to see if drivers stop at a stop sign. You have experiments in which treatments are applied in controlled conditions. For example, crop growth from different plots using different fertilizers. Let me give you another example of an experiment. It's something more like the example that they used over here under direct observation. You could make this into an experiment. And actually, I remember years and years ago reading about a kid who did this as their science project, actually. And I don't know exactly how they did this. But kid found a way somehow. Let me back up for a second. So this has to do with speeding. So I think what the kid did was got some, and probably had an adult helping. I doubt the kid did this, him or herself. They got something that looked like a radar gun and pointed it at cars as they drove by. And what they found was one day when they went out there and just watched cars, a lot of the cars were speeding, and I guess they had a way of measuring that. So that would be just a direct observation. A direct observation is where you, the observer, do not interfere at all with the results. However, on another day, the kid and his mom or dad went out and pointed something that looked like a radar gun at the cars, and it made the cars go slower. So at that point, it turns into an experiment because now the observer is getting involved. All right, so that action of pointing something like a radar gun at the cars, that would be considered a treatment. It's something that affects the results. And then finally, you have surveys or questionnaires. Subjects are asked to respond to questions or discuss attitudes. For example, emailing surveys to customers to assess service quality. Here's an example of a survey. Obviously, I'm not going to read you this whole thing. I'm just going to point out a couple of good things about it. To encourage respondents to participate, an effective survey will state its purpose in the beginning, which they've done up here. And then it's a good idea to ask personal demographic questions at the end when respondents feel more comfortable with the process. Of course, you always have to worry about bias in an experiment or a survey or anything else. It looks like here they're specifically talking about surveys. The manner in which survey questions are asked can affect responses. Bias can occur when a question is stated in a way that encourages or leads a respondent to a particular answer. For example, do you agree that the let me try that again. Do you agree that the current overly complex tax code should be simplified and made more fair? All right, so you can see there are a couple of issues with that question. The person asking the question has kind of inserted their own attitudes about it. They are stating within the question that the tax code is overly complex. Maybe not everybody agrees. And they're also implying that the tax code is not fair, which maybe not everybody agrees. And I see this all the time. You know, we're coming up on an election as I record this, and sometimes candidates will send out surveys, and really I don't think they're all that interested in the survey results. They're just using them as a way to collect money. And the questions in these surveys are so ridiculously biased. Candidate will send out an email, you know, with a survey. Do you approve of, you know, this person's, or what do you think of this person's job performance so far? And the choices are excellent, good, or okay. All right. Well, the people that don't like that candidate might wish that there were a couple of other categories that are not as good as okay. But again, they're really not interested in collecting survey results because these things always have an appeal for money at the end. So that's always what they're for. All right, this is really important. We're going to be coming back to this quite a bit. Two main types of data. There is qualitative data, also sometimes known as categorical data. Qualitative data is classified by descriptive terms. For example, marital status, political party, or eye color. Quantitative data is always in the form of numbers. Now, we're going to be breaking down quantitative data into a couple of smaller categories, things that can be counted and things that can be measured. But what those two things have in common is that they're described by numerical values. So some examples of things that can be counted are number of children, or defects per hour. How many defects per hour are there at a certain factory? Things that can be measured would be things like weight or voltage. All right. So these are measured characteristics. All right. So you have your qualitative and your quantitative data. And we're going to break down qualitative and quantitative into a couple of smaller categories. Let's start with qualitative. So qualitative data can be either nominal or ordinal. And so let's talk about what that means. Nominal data is arbitrary labels for data with no ranking allowed. All right. So, and the most interesting thing to do is, first of all, any kind of data that is in words is automatically either nominal or ordinal. All right. It can't be anything other than those two things. However, nominal and ordinal data can be numbers. So here's an example of nominal data as numbers, zip codes. Zip codes can't be put in any meaningful order. They're almost interchangeable with the names of cities, almost. So you would not do any math with those numbers. Another good example of nominal data is the TV channel number. All right, TV channel numbers like channel 3, channel 10, channel 13, they don't mean anything as numbers. All right, they are just labels. Now, you go up to ordinal level of measurement, and then ranking is allowed. However, there is no measurable meaning to the number differences. All right, so for example, education level, master's degree, doctorate degree, bachelor's degree, associate's degree, there is a meaningful way of ranking those things. All right. Now, moving on to Interval level, interval and ratio will always, always, always be numbers, all right? So at the interval level of measurement, differences between numbers are meaningful. However, there is no true 0 point, which means division doesn't make a lot of sense, all right? And I'll give you a couple examples of this because to make it easier to understand. So the example they give for interval level is the calendar year, like 2018 or 2019. And actually, there was no year 0. Did you know that? There was the year 1 BCE, before the Common Era. And then the next year would have been the year 1 CE, Common Era, all right? No year 0. However, what's even more important is it wouldn't make any sense to talk about the year 2000 being twice the year 1000. That just doesn't make any sense. Another good example of interval level is temperature, all right? Degrees Fahrenheit, degrees Celsius, it doesn't matter. Now, there is such a thing as 0 degrees Fahrenheit and 0 degrees Celsius, but that number was just sort of chosen by somebody. It doesn't have any mathematical meaning, all right? So if I walk outside and it's 90 degrees, it would not make any sense to say that that's twice as hot as if it was 45 degrees. That just doesn't make any sense, okay? Now, when it does make sense to do that, then you're talking about ratio level. At ratio level, differences are still meaningful, and so are ratios. And there is a true 0 point. So another way to sort of differentiate between ratio and interval, at interval level, you often have negative numbers. At ratio level, you don't, all right? You have a true 0 point, and that's the beginning. So the example they're giving is income. A person's income could be $48,000, or if they don't have a job outside the home, maybe their income is 0, all right? But there is a true 0 point. And it does make perfect sense to say that somebody who makes $48,000 a year has twice the income of somebody who makes $24,000 a year. That makes total sense, and that makes that ratio level. So hopefully that makes sense. All right, another way of distinguishing data, you have time series versus cross-sectional data, and I have a good example for that coming up. Time series data are values that correspond to specific measurements taken over a range of time periods, versus cross-sectional data, which is values collected from a number of subjects during a single time period. All right, so here's a great example. We have unemployment rate data from 2013 through 2017. Notice the source here again at the bottom. So if I were to look at the unemployment rate for the whole country overall, from the years 2013 to 2017, that would be an example of time series data because I'm looking at the same group, the United States, unemployment rate measured at different times. However, if I were to focus on the year 2013 and compare the US overall with California, Michigan, Texas, Florida, that would be an example of cross-sectional data because I'm looking at those all at the same time, okay? Here we have a time series graph of US unemployment rates, 2013 to 2017. And below that, I have a cross-sectional graph of 2017 unemployment rates, all right? We're going to be talking more in chapter 2 about different kinds of graphs and when each one is, appropriate to use. But that gives you a little flavor for that, I think. All right, section 1.3, we have branches of statistics. First, we have descriptive statistics, which is actually the first thing that we're going to be doing in this course starting in Chapter 2. And that is collecting, summarizing, and displaying data. And then later on this semester, we're going to talk about inferential statistics, which is making claims or conclusions about the data based on a sample. And I'm not sure that we're going to be doing this third thing in this class, analyzing past data to predict future values and make decisions. But that is a thing that people do. All right, populations versus samples. A population represents all possible subjects that are of interest in a particular study. A sample refers to a portion of the population that is representative of the population from which it was selected. So here you have what we call a Venn diagram, showing that the sample is a part of the population. And why this is so important in statistics is because populations are usually too big to study, everybody. And so what we do instead is we collect a sample and we hope, and we really try hard to make this happen, that sample is representative of the population. So for example, suppose my population of interest was all students at Stan State. And you probably know that Stan State is majority female students. I can't remember the exact ratio. It's at least 60-40. So if I was going to have a sample of, say, 100 students, I would, hope that sample is also majority female, all right? And hopefully about the same ratio. So just any characteristics you can think of the population. 10% of students are business majors, 15% are liberal studies majors, whatever it is, you try really hard to make those same things true for the sample. Okay. All right, parameters versus statistics. Told you there's a lot of vocabulary in this chapter. All right. A parameter is a described characteristic about a population. A statistic is a described characteristic about a sample. And I don't think this was planned, but everybody appreciates this because it makes it very easy to remember. Notice that parameter and population start with the letter P. Statistic and sample start with the letter S. So that makes it easy to remember which one's which. Okay, so values calculated using population data are called parameters. Values computed from sample data are called statistics. All right, inferential statistics, again, is making claims about a population by examining sample results. So for example, you have an observed sample statistic. Sorry, let's say that I ask 100 students, how do you feel about online classes? And 60% of them say they like them. The inference would be an estimated population parameter. All right, so unless I ask every single student at Stan State how they feel about online classes, I don't know exactly what that percentage is. But later this semester, we're going to be talking about how 60% would be your estimate based on your sample, and you can attach a little margin of error to that. 60% plus or minus 3%. Okay. All right, here we have a figure that talks about using inferential statistics for quality control purposes. So let's say we start by assuming the unknown average weight per box of cereal in the population is 18 ounces. So we select a random sample of cereal boxes from the population. We calculate the sample average, which comes out to 18.2 ounces. Using inferential statistics, we determine that the probability of the actual population average being 18 ounces is less than 1%. If the sample average is 18.2 ounces. So based on that, I would conclude that the actual population average is greater than 18 ounces. I believe, so this is my first time using this book. I think this is the kind of thing we're going to be doing in chapter 9. I believe it's chapter 9. All right, and finally we have ethics and statistics. It's a dangerous world of data out there. All right, so one thing that can happen is you can get a biased sample, which is a sample that does not represent the intended population. That can lead to distorted findings. Biased sampling can occur intentionally or unintentionally, and results can be manipulated by how we ask questions and who is responding to them. So you saw that example earlier about the survey question about the overly complex tax code, right? Ways of misusing statistics. One way is changing the graph scale. Notice that these two graphs are technically showing the same information. However, person looking at these might not get the same message out of these. And actually, I see at least one problem with both of these. Right? I do like the one on the left, maybe just a little bit better, although I'm not sure. So, of course, the one on the left, the vertical axis just goes from 4 to 8%. And so the decrease in the unemployment rate from 2013 to 2017 appears a lot more dramatic, right? Now, if you make the vertical scale 0 to 50%, this almost looks like a flat line. It almost looks like there was no change in the unemployment rate. My preference would actually be to make the vertical axis go from 0 to 8. Because actually, I think this one is a little misleading too. It kind of makes it look like that the unemployment rate in 2017 was something like maybe 1/7 what it was in 2013. And of course, that's not true. Another problem is choosing a sample that is not representative of the population. So to avoid that problem, just always try to randomly sample from the population. And that's it. That is all of chapter 1. So we'll see you next time. And like I said, 1 video per section, starting with the next one. All right, we'll see you then.